Okay, so let me start by thanking the organizers for inviting me here, Thangadurai, Shauligun and Purushottam. I really feel great to be here on the occasion of felicitation of Professor Ramamurthy, whom perhaps I can consider as one of my early teachers in this subject. In the instructional school in Hyderabad in '99, you gave a series of lectures, and soon after, in Jan 2000, in HRI also, lectures on p-adic analysis. And also, actually this is the first, I think your book on problems in algebraic number theory was fresh from the oven at that time, and all of us were gifted a copy. And so it is the first Springer GTM that I owned. And also I think you quoted Vivekananda there, it's practice first and knowledge afterwards, so that was one of the inspiring lines. Okay, so the title is on the degree of certain local L-functions, and it's joint work with my student Amiya Mondal. Okay, so let's start from the simplest of L-functions, the Riemann zeta function. When real part of S is greater than 1, it's defined as summation 1 by n power s, which has the Euler product expansion. So there is this local in my title, and I just want to give some examples before we start. So this has the Euler product expansion as 1 by 1 minus p power minus s. And the associated local L function at prime p is just this, which is 1 by a polynomial in p power minus s. And as a polynomial in p power minus s, it's a linear polynomial. It's a polynomial of degree 1. This is the degree that I am talking about in the title. Okay, so let's take one more example, the Dirichlet L function. So if you have a Dirichlet character, and consider the associated Dirichlet L function, which has the Euler product expansion like this. So once again, it's the local L function is 1 by a polynomial, so reciprocal of a polynomial in p power minus s of degree. Now it could be 1 or 0 depending on chi p. So it's 1 if p does not divide n, and if p divides n, this goes away. So it's just a constant function 1, in which case it's degree 0. Let's do just one more example, the Hecke L function associated to a modular form. So if you have the standard things are, if a Hecke eigencusp new form with normalized coefficients level n and central character omega, then you have the Hecke L function, so Fourier coefficients by n power s, which has an Euler product expansion. So the associated L function, the local L function at p is 1 by this polynomial. And here the degree of the polynomial is, so it's p power minus s square here, so it is 2 if p does not divide n, and if this part goes away, it could be 1, and that happens when p exactly divides n, and if p square divides n, then all these will go away and it will be degree 0. So degrees can be 0, 1 or 2 in the modular form case. So this is the degree in the title of the talk. So these are the local L functions and the corresponding degree. So we want to ask a more general question. So the case of the Riemann zeta function and the Dirichlet L function was the degree 1 or 0 situation, and that one can think of as characters of GL1AQ adults over Q. And the next one, the Hecke L function, one can think of as similar theory for GL2AQ. And so what we now do is we will go to any number field F and take, this is just as part of the introduction. I will have no number theory in the sense no global fields from the next slide onwards. So if F is a number field and if pi is a cuspidal automorphic representation of GL and AF, it's a natural generalization of these pictures, GL1, GL2, and so GL and AF. And then pi can be written as a restricted direct product of local representations. So each pi v will be an irreducible admissible representation of GLN over a local field. And there are various ways to attach a local L function associated to each finite place. So let's assume that it's somehow defined, Ls pi v. And once again, this will be 1 by a polynomial in q power minus s, where q is the residue cardinality of fv. Okay, so our interest is in that question, what's the degree? And from the examples that we have seen, so and the global L function will be a product over all these local L functions. So degree of Ls pi v, so in all these examples, most often it was the maximum possible, right? When p does not divide in, so almost all the places it was the maximum possible. For GL2 it was 2. In the other case, Dirichlet L function, mostly it was 1. And otherwise it could come down, and it did take 1 and it took 0 at a particular place. So similarly, here also, the degree is n at almost all v. It will be the maximum possible n, and these are exactly the unramified places. P does not divide n, that picture, so the unramified places. And at all the other places it could be, so earlier it was 1 and 0, later it was 2 and then 1 and 0, so similarly it could be n minus 1 to 0 anything. So and it's between 0 and n minus 1 at all the other places. So we are going to come to the local theory from the next slide, and these were the local representations, but this category of representations is understood once the so-called supercuspidal representations are understood. So if you understand most of these questions for supercuspidal representations, then many other things will automatically follow. So we will soon focus only on the basic building blocks, supercuspidal representations, which corresponds to p square dividing n in the Hecke case and p dividing n in the Dirichlet case, in which case the degree is 0. So that's what happens here also. So this can be 0 in many cases. In particular, if you are focusing only on the basic building blocks of this theory, then it is constant function 1, as in the early examples. So the p square dividing n case, if it is supercuspidal, it will be the p square dividing n case, and you are getting constant function 1, which is degree 0. Okay, so in that sense, if I focus only on supercuspidal, this question is done, right? I mean, it's constant function 1 and nothing more to do. So we will consider slightly more general L functions, where I assume that the representation is supercuspidal and ask whether one can get what the degree is. So that's the point of the talk. So let's just remember that for a supercuspidal, it's a degree 0. A degree is 0. Degree of the local L function is 0. So from now onward, F is a p-adic field, one of the local places, and pi is a supercuspidal representation of GL and F. Once again, I'm focusing on supercuspidals because once we understand supercuspidals, all the other things will be automatically means with some work understood. So the standard L function of pi is what we had considered, just Ls pi, and that is constant function 1 and has degree 0. So there are many other natural L functions associated to pi, and that's what we want to focus on. So pi is supercuspidal, and some other natural L functions associated to pi, and what can one say about the degree. So what are some of these natural L functions that we can consider? One is the so-called Rankin-Selberg L-function, which has already appeared in many talks in this conference, and another is a closely related L function called the Asai L-function. And another one is the symmetric square L function, and one more maybe exterior square L function. So we will focus on these. Okay. So let's look at the Rankin-Selberg story. What happens there? So we already have GLN F and one supercuspidal representation pi of GLN F already fixed. And now consider one more GLMF, let us say, and take another supercuspidal tau of GLMF. So Rankin-Selberg, you will have two things. And then once again the Rankin-Selberg L function is it is once again constant function 1, except in one sort of situation, which is that m is the original n, and this second one that you have taken is, so this notation is the contragradient representation. You have a pi and you have the dual to that, pi dual. So except in this case, it's constant function 1, except up to a twist by an unramified character. So this is constant function 1 unless tau is pi dual tensor an unramified character. And in that case, it's a theorem or an observation due to Bushnell and Kutzko in their book in 1993 that you can actually say what this degree is. And it is some simple thing. So this n is the GLN n, and this E is a certain ramification index canonically associated to pi. So it's a very natural way to attach one E to this pi. Let's not get into the definition. We don't really need it later. The only point here is there is a simple expression for the degree of the local Rankin-Selberg L-function. Most cases it is 1, and the only time it is not degree 0, the answer is this, and this E depends only on pi. Okay. It's just 2-3 lines proof. It's an easy observation, and let's just observe. So maybe for the for those who are really interested to keep something in mind, it's easy to think of these under the local land-length correspondence. If you think of these as n-dimensional representations on the Weyl side, what all one is saying is if you take the representation corresponding to pi and corresponding to pi dual, in that tensor product, you are counting how many times an unramified character is coming. As we have seen in our examples, only unramified characters are contributing to the degree of the L function. So how many? So it's a group theory, it's a representation theoretic question. So in this particular case, it's not surprising that there is an easy answer, because what one is counting is if you take the n-dimensional representation pi of the Galois group and its dual and take the tensor product, so that will be a direct sum of many things, and how many unramified characters are constituents there, right? Now the point is the characters coming in such a tensor product of this shape, something tensor its dual, there is a nice structure to this in the sense that they form a group. Okay, so that's the observation, that if pi tensor chi is pi and set of all characters you take, so this number, the final answer here is exactly the number of unramified characters here. Okay, but the point is all such characters if you take, that's obviously a group under multiplication of characters. So there is some more structure to it. So though it's just counting, there is a group structure to it, and somehow that makes things very easy to do this counting. All those characters form a group, and all those unramified characters in which one is interested forms a subgroup. After all, it's a group, and therefore, just remember this fact. Okay, so this is the Rankin-Selberg story, complete picture. Most of the time, it's a constant function one. The only time when it is not, there is a simple answer, and you expect a simple answer because there is much more structure to this question. The characters which contribute to the L function, they form a group. So let's look at the other 3 L functions, Asai, sim square, and exterior square. So once again we assume, so associated to pi, a supercuspidal representation of GLN F. So this is the symmetric square L function, LS pi sim square, LS pi exterior square, the exterior square L function. All these can be introduced in many different ways. And to define Asai, you need not just one field, but a quadratic extension of fields. So let's take, I was just thinking that, at lunch, there was this discussion between Raghuram and Professor Murthy about whether you should take a field and its extension or, take the subfield. Never before I have written like this. I always took an F and took a quadratic extension. This is the first time I'm writing it like this, take an F and take something inside. Anyway. So a quadratic extension of, so if you have a quadratic extension and then associated to pi of GLN F, there is this, the point is in order to define this, I need this picture of a quadratic extension. So these are the L functions that we want to consider. And maybe a quick aside that very generally you can consider L functions of the form LS pi comma something. Okay, how does one consider such things? So once again, so consider this as the Galois group of F, and under the Land-Lance correspondence you have, so if you have a representation of GLN F, you have an n-dimensional representation of the Galois group, and if this is that n-dimensional representation, and suppose you have one more representation of this group, let's say R is a representation of GLN C, an m-dimensional representation, then corresponding to this you have an L function Ls pi comma r. So very generally you can construct L functions like this, and these are all instances of this. So you are taking the sim square representation of GL and C, so their m will be n times n plus 1 by 2, and exterior square their m will be n times n minus 1 by 2, and in the Asai case, you will finally have, it will be valued in GL n square. If you started with n, it will be valued in GL n square. Not very important for what we are going to say. Okay. The only point that I'm trying to say is very generally you have L functions of the shape L, S, with a complex variable, pi, the starting supercuspidal representation, and R, where R is some representation of GL and C. And what are we interested in? In trying to find the, so all these will be 1 by a polynomial, and we are interested in trying to find the degree of that polynomial in all these situations. So in this particular notation, the standard L function which we started about at the very starting is corresponding to the identity map from GLNC to GLNC itself. Okay. So these L functions, maybe I have enough time, I think. So these L functions arise in various ways in various places. For example, the degree of Ls pi r, where r is either Si or sim square or exterior square. I'm focusing only on that. R is the tensor product in the Rankin-Selberg situation. So GLN cross GLM to GL Mn. So R is sim square, exterior square, Si. Because the Rankin-Selberg was a complete neat picture. It's a story that's finished. So we will focus only on these three. So this has often several important interpretations. For instance, so let me just give some background. So for instance, in the works of Shahidi, Goldberg, Kim, etc., these L functions typically detect Langlands functorial lifts from classical groups. So, once you take it for granted, the degree of the L function is in some sense how many unramified characters are coming. So it's some things about pi and its unramified twist, and in that way of looking at it, for an irreducible supercuspidal representation pi, the degree of Ls pi r is nothing but, so it's either the number of unramified twists or half that number of pi, depending on which group you are on, which classical group you are on, which are Langlands functorial lifts from classical groups. So it's so this degree is counting something in the context of Langlands functoriality. So this is Shahidi 92, and so this may be, I think, sim square and exterior square, and this will be the unitary group situation, which is the Asai situation. So orthogonal, symplectic, and unitary. Another place where this has a nice interpretation is what is called distinguished representations, a theory of that, relative trace formula and period integrals, that kind of thing, the local aspects of such a question, and what does this count there? Once again, so I'm talking only about the Asai L function here, and then its degree counts the number of unramified. So remember, whenever I talk about the Asai L function, there are two fields. There is a quadratic extension f over f naught, and this degree is counting the number of unramified characters mu downstairs, f naught star, for which there is this notion of distinction, and for which pi is mu distinguished with respect to GLN f naught. So it's counting, something in that area of distinguished representations. What all I'm trying to say is this degree naturally comes at various places. So this is some work with Anthony Cable and Rajat Tandon. If pi is a supercuspidal representation, so let's do something similar in spirit to this. For the exterior square L function, again it counts something, what is called a Shalaika functional. So this will be half the number of unramified characters mu of f star, such that if you tensor with mu, this admits the so-called Shalaika functional, and this will follow from either the work of Jiang, Nian, and Kin, or Pramod Kevat and Ravi Raghunathan. Okay, so that was an aside. So recall once again, Ls pi, the standard L function, because we assume pi is supercuspidal, has degree 0, and the Rankin-Selberg one is mostly degree 0. The only other case where there was a neat answer to that. And the other remark in this context was this was kind of easy because there is more structure to that question, because all the characters itself coming in the tensor product formed a group. In particular, the unramified characters formed a group. So we want to compute the degree of LS pi R, for which, so if you want to compute this, in many cases it may be 1, in which case degree is 0. So you can assume it is not 1. Only then you have to start counting the degree. And so you can assume that it has at least one pole, which contributes to the degree. So you can assume it has at least one pole, and by doing some shifting, you can assume that it has a pole at s equal to 0 in order to start the question. So without loss of generality, you can assume that this has a pole at s equal to 0. So what does this? So this in particular will imply that pi is its own contragradient. It's a self-dual representation. In our first two examples, R is sim square or exterior square, and in the Asai case, this will imply that, so now you have a quadratic extension f over f naught, and this implies that pi bar is pi dual. So only unexplained thing here is a bar. It is f over f bar, and bar is the Galois conjugation. Okay. So the only places where you have to there is any question to ask, you are there is some extra information about your representation automatically. And now that we have these situations, either you are in the self-dual situation or you are in the conjugate self-dual situation, we have the following identities. So the Rankin-Selberg L-function for pi and the same pi is the product of sim square L-function and the exterior square L-function, and we are in this situation. So we already have achieved something. The left-hand side, we actually know the answer, what the degree is. So though and we want to find the degree of this and this, but at least we know the sum of those degrees from this identity. And similarly, we have an identity Ls pi cross pi bar is the Asai L-function and the so-called twisted Asai L-function. It is also the Asai L-function, but there is a twist here, and this is so associated to, again, you have f over f naught, and there is a quadratic character of f naught associated to this extension, and you can take any extension of that and call it kappa. Okay, so it's a product of two Asai L-functions. So once again, this we know is some number from Bushnell-Kutzko observation, and therefore we know the sum of the Asai degree plus the twisted Asai degree. So that much we have. So in some sense, for free, we are getting some information from here. So we know that LHS is n by E. So n is, if pi is GLN, this is that n, and E is naturally associated to pi, some number naturally associated to pi. One has to be a bit careful. Here it is n by E. Here also maybe it is n by E, but there is one more possibility, because you have f over f naught. Whether that is ramified or not will also play, because I am finally counting it as a polynomial in q power minus s, but the q itself may be q square in the unramified case, right? So it is so q power minus 2s, that extra 2 might come. So it is either n by e or 2n by e, and 2n by e exactly in this situation when that f over f naught is unramified. Otherwise, here also it's n by e. Okay. So some information we already have by that observation. The latter occurs, this occurs exactly in the case where in the second identity when f over f naught is unramified, otherwise it's n by e. That's what I was saying. So we are finally interested in this degree, but some of the degrees we have a hold on from the Rankin-Selberg picture, which was an easy picture anyway. And similarly, degree of the Asai L-function plus the degree of the twisted Asai L-function is 2n by e if f over f naught is unramified, n by e if f over f naught is ramified. This much we know. Okay. So now what we want to say is the sum we know. We want to say individually what it is, and let me state it as a result. So in the first two cases, so I will deal with sim square and exterior square together and Asai separately. So in the sim square or exterior square case, we have the identity this plus this is n by e, and what we want to say is the only possibilities are this right hand side n by e is either n by e plus 0, right? So this has degree n by e and this is constant function 1, or the other way, this is constant function 1 and this has degree n by e, or it equally divides. n by e is n by 2e plus n by 2e. There's no other possibility. Okay, so this total thing, they could have been, I mean, a priori it could have been divided in various ways, but these are the only possibilities. Similarly, in the Asai case, you may have two things, and the only possibilities are, in the 2n by e case, this is the only possibility. Each individual, the Asai L-function and the twisted Asai L-function has degree half of the total. In the other case, when f over f naught is ramified, this n by e, exactly like in the earlier result, there are only three cases. Either it's n by e plus 0, or 0 plus n by e, or it's half-half. There's no other possibility. Okay, so that I mean, this is what I wanted to say. Maybe I will just indicate what can be a potential difficulty in this question compared to Rankin-Selberg, which was after all a 3-line proof, and how to overcome that difficulty. So first observation is, if n is odd, nothing is difficult here. After all, you know, there is no way you can divide by 2. So I know from this itself it should be clear that it should be some of the EC cases, and that's kind of clear even from the starting. For example, when n is odd, this thing will not exist. This will not be there. The exterior square L function will be a constant function 1 automatically, and therefore there's nothing to consider. The full n by e goes to 1 of this, so it's n by e plus 0. And so in that case it's EC, it's an obvious statement. Or in the Asai case, if f over f naught is, in the Asai case, in two cases it's rather obvious. One is, once again, n is odd. So in all cases, n odd or even, this is EC. In the unramified case, essentially the only point here is, if you start with a character and you have this f over f naught, and the only way you go to f is by composing with the norm map. And if that compose with norm is unramified, then there are two characters which goes to this character there, and both have to be unramified because the extension is unramified. So for some very simple reason, this is also obvious. And once again, when n is odd, you can't divide by 2, so it has to be this or this. And that also is easy, because when n is odd, central character captures in some sense much more information than when n is even. So for some basic representation theoretic or field theoretic reasons, many of these parts are kind of easy. There's nothing to prove. So if n is odd or n even or odd, but f over f naught is unramified, these results are quite straightforward. So the only place where one will have to do some work is when n is even, and our approach is to prove the second theorem. In the Asai case, when n is even, so you will have to show it's either n by e plus 0 or 0 plus n by e or n by 2e plus n by 2e. So establish that. And what does one do there? So assume that both have non-zero degrees, otherwise again there's nothing to show, right? It's either this plus 0 or 0 plus that. So assume both have non-zero degrees, and in this case we want to show that both of them have the same degree. It's half-half. And here the idea is to exhibit an explicit bijection between poles of this L-function. So you give a bijection between the poles that contribute to the first one to the poles that contribute to the second one. Of course, this is not saying much after all, you know, I mean, if two sets have same cardinality, there is a bijection, but in a rather explicit way one can give after doing some work. That's the point. So how does one do that? So once again, in the Rankin-Selberg case, everything was easy because there was some group there was a structure of a group to all the characters there. Whereas, so I did not make that remark, but in the sim square or exterior square or the Asai case, the corresponding representation, if you take on the Galois side of the correspondence, there is no, I mean, this is not true that even if you assume the trivial character is there so that you have the identity element to talk about, it's not true that if chi1 belongs there, chi2 belongs there, then the product belongs there. So there is no obvious structure. So, but on the other hand, that much we don't want for this particular question, because after all, not all characters contribute to the degree, only the unramified characters contribute to the degree. So we can still achieve something if we can say that, all right, not all the characters all the characters in this representation may not form a group, but at least if all the unramified characters form a group, that's all that is relevant for any question about L functions. Okay, so that's what we prove, that though not all characters which come in these representations form a group, the subclass of unramified characters actually form a group under multiplication. But now it's not a purely group theoretic statement or something. There's not purely a representation theoretic statement. There's a little bit more information required. And the way one does is, earlier also I said that this Asai L-function is related to this theory of distinguished representations. So, and this degree is counting something. So convert the problem to a problem there, and there you have some more tools, and use those tools to show that unramified characters coming in this representation do form a group. So that's the idea. So this group theoretic statement is achieved by relating these poles with the theory of distinguished representations, and this can be done by combining two pieces of work. One is with Anthony Cable and Rajat Tandon, which I quoted earlier, and one also needs, in order to go to the Galois side, some more information about these Asai L functions, and that was work with C.S. Rajan. So one has to use both in order to convert the problem to this distinguished representations. And then another ingredient is, so you have translated the problem, but in order to say that in the Asai left, if chi1 and chi2 unramified appear, chi1, chi2 also appear, you need some more tools to do that. And that is another way of characterizing distinguished representations via the so-called local epsilon factors, the local root numbers. And this is some work which was done by Young Bin Oak at Columbia. He was a student of Jacques at Columbia. I think he quit mathematics later. So you can translate the problem in order to count this degree to the theory of distinguished representations. Once you reach that world, you have some other computable ingredients there, and so that information also one has. And then finally, unramified characters, to bring that to the picture, the point is that these epsilon factors are well understood under twisting by unramified characters. So together with the knowledge of the behavior of these local epsilon factors under unramified twisting, one can show that one can put a group structure to the poles of the Asai L-function. And once you have such a nice structure, it's easy to give an obvious bijection between the Asai and twisted Asai, dividing the degree to half-half. So that's the idea. And how does one do sim square and exterior square? There is no natural way in which some epsilon factor kind of thing is related to sim square having a pole or exterior square having a pole. And our tool in the earlier case was to bring epsilon factors which are understood very well under unramified twisting, and use that to form, say that a certain set forms a group or something like that. So here there is nothing like that, but now having achieved this in the Asai case, one can bring the problem of sim square and exterior square to that case. So that can be done. So I will just write down the identity. So you can think of all these as n-dimensional representations of the Weil group, of the Galois group, and there one can, so one has standard identities of this form. So in order to do a sim square question, if you have sim square of an induced representation, say from some group H to G, then it is induced of the sim square of this plus the Asai representation of that inducing thing. So somehow, the sim square of something is induced of sim square of a lower dimensional thing and plus some Asai information. So if you know enough about Asai, perhaps there is a way to use that information and conclude the sim square question. Similarly, exterior square. So this identity relating exterior square with the twisted Asai is what I wrote kappa earlier. So there is a way to do that, and that's what one does. So here H is the Weil group of the quadratic extension, and G is the Weil group of the base field, and rho is the representation corresponding to the starting supercuspidal pi. So it's an irreducible representation here, and this R is the Asai representation. So having done the problem in the Asai case, there is a way to bring the sim square exterior square problem to the Asai case and use the information there to show that unramified characters coming in sim square or exterior square also will form a group, and then you have again a nice bijection dividing it half-half. And note that because in the odd case it was easy, this is fine, because this will be an even dimensional representation. So you are on GL2n, and you have only the GL2n case to consider because n odd anyway was obvious. So these identities can be made use of. Okay, so I think it's ending. So this remark, I think I repeated enough. Maybe there's no point in repeating once more. So this is what, in some sense, made the Rankin-Selberg computation easy. And not having such a structure obviously is what is making this problem for Asai and exterior square and sim square kind of difficult. But then there is a way to get around it since you have to focus only on unramified characters. So the difficulty with LS pi r in these cases is that it's not obvious that there is a structure to the poles of LS pi r because there was no structure to all of the characters. But then using some finer arithmetic information, such as local root numbers, one can put a group structure, and once you have that kind of a structure, it's easy to establish this. Okay, I'm done.